Hi, welcome back. So far, you have learned how to build and train a logistic regression model. But how do you know if your model is actually performing well? This is where the model testing comes in. Think of it as your model's final exam, a chance to prove if it can handle real world data. Model testing involves evaluating your model on new, unseen data to see how well it generalizes. Why is this important? Because testing reveals the true performance of your model and catches potential issues before deployment. Always make sure your model is ready for the real world. Let's look at a practical example, a spam detector. Imagine your logistic regression model has been trained to distinguish between spam and non-spam emails. But how do you know if it's ready to handle new emails? Testing on new, unseen emails, both spam and non-spam, helps assess its generalization ability. The model analyzes each email using what it learned during training to make predictions. If an email's probability of being spam is above a certain threshold, it's flagged as spam. Otherwise, it's classified as not spam. Finally, we analyze the results to see how well our model performs. Before testing, let's review what we need. We use data that model hasn't seen before to see how it can handle new scenarios. X validation is our feature matrix with dimensions m cross n, where m is the number of samples and n is the number of features. For example, if we have 100 samples with 5 features, then each X validation would be a 100 cross 5 matrix. Y validation contains the true labels for our test data, showing the actual outcomes for each sample. If there are 100 samples, then Y validation would be 100 element column vector, with each value as 0 or 1, indicating if it's a spam or not a spam. Theta, the weight vector, learned during the training with dimension n cross 1, one weight for each feature. For 5 features, theta is a 5-element vector, each weight indicating a feature's importance in the prediction. To make predictions, we first use the sigmoid function, which converts linear prediction into probabilities between 0 and 1. For example, a higher probability suggests spam, while a lower one indicates non-spam. This transformation helps turn continuous scores into probabilities that are easier to interpret. Next, we use a threshold to convert these probabilities into binary predictions. If the probability meets or exceeds the threshold, the model classifies the input as one category, like spam. If it's below, it classifies it as another, like not a spam. In our spam detector example, if the probability is 0.5 or higher, the model predicts it as spam. If it's lower, it predicts not spam. This approach allows logistic regression to make clear, actionable decisions based on probability score. To evaluate our model's performance, we use a confusion matrix, which compares the model's prediction with the actual outcomes. It visually breaks down where the model got things right and where it made mistakes. Accuracy is a key metric. We derive from the confusion matrix. It calculates by dividing the number of correct predictions, true positive and true negatives, by the total number of predictions. This gives us an overall sense of how often the model is correct. Accuracy is expressed as a score between 0 and 1, or as a percentage. A perfect accuracy of 1 or 100% means every prediction is correct. In our spam detector example, the model achieved an accuracy of 95%, correctly identifying whether emails were spam or not 95% of the time. While that's a strong result, there is always room for improvement, especially if important emails are mistakenly flagged. However, Accuracy alone doesn't capture everything, particularly with imbalanced dataset. That's why other metrics like precision, recall, and F1 score are important. Precision measures how often the model's positive predictions are correct, while recall shows how well it captures actual positives. And the F1 score balances both. It highlights how well the model handles the trade off between missing positives and avoiding false alarms. So, while accuracy is a good starting point, precision, recall, and F1 score give a full picture of model performance. We will explore these metrics in more detail in the next lecture. So, what do these results mean? If accuracy is low, the model is performing poorly and may not be useful. It could be close to random guessing. An accuracy that's moderate shows the model is catching some correct predictions but still missing quite a few. There is a room for improvement in making the model more reliable. Good accuracy indicates that the model is performing well and correctly classifying most cases, making it dependable for practical use. However, extremely high accuracy can be a red flag for overfitting. This means the model might be memorizing specific data patterns rather than learning general ones, which could lead to poor performance on new data. Accuracy is just one piece of the puzzle. Always consider it alongside other metrics and observe how the model behaves with the new data. The goal is to achieve a balance that ensures strong performance both in testing and in real-world scenarios. Each loop through this process brings improvement. Remember, testing isn't the end of the process. It's a tool for continuous improvement. Use your test results to tune the hyperparameters like learning rate or number of iterations. If accuracy is low, you might need to revisit your feature selection or consider a more complex model. For example, a lower learning rate may help the model learn more carefully, avoiding overshooting the optimal solution, while the right number of iteration ensures the model trains adequately without overfitting. To wrap up, let's review the key points. Testing helps evaluate your logistic regression model's performance on unseen data. The process involves computing the sigmoid function, making prediction, and calculating accuracy. Use accuracy as your key metric, but don't rely on it alone. Interpret your results carefully and use them to improve or tune your model iteratively. Remember, the goal is to create a model that generalizes well to new data, not just well on your training set. In the next video, we will dive into other important metrics used in the testing process. So stay tuned.